In order to succeed in chemistry, we must measure things, convert things to other measurements, and be successful in our labs and tests and other problems. In order to do this, we must understand three basic concepts: measurements, conversions, and dimensional analysis. First, we're going to look at measurements. In chemistry, we use the SI system. Here, derived units are built from basic ones. So basically, there's a basic unit that we use, and we add a prefix in order to change the size of that base unit. Just to look here is a chart with some of the basic quantities and SI units that we use in chemistry. Not all of them, but most of them. For example, area would be meters squared, velocity would be meters per second, density would be grams per liter, length would be meters, mass would be kilograms or grams, time would be seconds, or S for seconds, temperature would be K, which stands for Kelvin, and volume would be liters. Moles would be mole, as an abbreviated form. With the exception of moles and seconds, in Kelvin, we can add prefixes in order to change the size of these units. For example, some of these prefixes are milli, centi, deci, deca, hecto, kilo. And these units increase by increments of 10 each time you move up, or decrease each time you move down a unit, or prefix. So measurements come in two forms: qualitative, which are the things you observe that a number value can't be put to, and quantitative, where there's a number value that describes something. For example, you have 6 liters of hydrochloric acid. This is where the SI units come in. For example, I just used liters, and with that number of 6, there's 6 liters, which means that the volume of the hydrochloric acid would be in liters. So then we move on to conversions and dimensional analysis. In order to convert or change between one unit to another, we must use dimensional analysis. Basically, in dimensional analysis, you understand that the fact that units for physical quantities can be changed by using conversion factors and multiplication. We're going to now look at some examples. Here's a very basic one, not including much math, but just gets the concept across. So you have 3 ducks equals 4 horses equals 6 cows equals 3 ants. If you have 6 ducks, how many horses do you have? So first we're going to ask ourselves a few basic questions. What do you know? You know that you have 6 ducks, and that for every 3 ducks, you'll have 4 horses. So now you can change that, which I just said, into an equation that will give you the number of horses that you would have if you had 6 ducks. So first you start with 6 ducks, and you then multiply that by a conversion factor. The conversion factor can be found within the given information. Here, for every 3 ducks, which would go on the denominator, so the ducks cancel out, equals every 4 horses. The 4 horses would go in the numerator, so you end up with that unit in your answer. So it ends up being 6 ducks times 4 horses over 3 ducks. The ducks cancel out, and you're left with the equation of 6 times 4 horses over 3. When you multiply that out, you get 8, and you are left with the unit of horses. So now we're going to move on to an example using stoichiometry. A bit more complex, but I'm pretty sure we can all do that. So this is the actual equation that I used from my stoichiometry video. However, we're going to use it again here just to get the point across. So C3H8 plus 5 oxygen yields 3 carbon dioxide plus 4 H2O. So what we're looking at is how many moles of carbon dioxide are formed when 40 moles of oxygen is consumed while burning propane. So first we have to look at what we know. We know that we have 40 moles of oxygen, so that comes in first. And then we have to use a conversion factor from the balanced chemical equation to get to the moles of carbon dioxide that we want to have and want to know. So as we look at the equation, we find that for every 5 oxygens, which would go in the 5 moles of oxygen, which would go in the denominator, so the oxygens cancel out, and equals 3 moles of carbon dioxide, and that 3 moles of carbon dioxide would go in the numerator, so we end up with that unit. When you multiply it out, it comes out to 24.0 moles of carbon dioxide, and you just have to remember that the moles of oxygen cancel out, so the moles of carbon dioxide can be formed in this equation. So now we're going to look at a simpler problem, just like converting simple things like seconds to a day. So how many seconds are in a day? First, we have to know what unit of measurement we want in the end. So we want seconds per day. So what do we know? We know that for every 60 seconds, there's 1 minute. For every 60 minutes, there's 1 hour. And for every 24 hours, there's 1 day. So now we start with the 60 seconds per 1 minute, and we turn the rest into an equation. So then we multiply that by 60 minutes per an hour for every hour, and the minutes cancel out. So now you need to get rid of that 1 hour in the denominator and get 1 day to be in the denominator. How you would do that is use the next step. 24 hours over 1 day. So the hours will cancel out and you'll be left with 1 day. So once you cancel them all out and cross them all out, you see that you have seconds in the numerator, day in the denominator. That's exactly what you want. So now you multiply and divide that all out, which comes out to 86,400 seconds per day. So for every single equation that you need to do in chemistry, you use this general method in order to convert units. So now you can convert between units and also keep track of the units and the chemicals or ideas that go along with it. For example, that stoichiometry problem where we held on not just to moles, but the moles per a certain substance, which would allow us to get there. So now you can go out with whatever equation you want, apply this general method, and be able to convert between the units and measurements that we talked about earlier.